In the last video we worked out how to take our two natural relationships, power relationships and exponentials, which if we did an experiment on we'd get a curve, and how to create straight lines that we could find the values, constants are for the relationships in. And we did that by logging the relationship equations, matching up the terms for the gradient and the intercept or constant, and then we knew how to read off from a graph. So it was either going to be a log graph on this side, because I've got a log here and a log there, from there this equation up here and here, or a log x graph here to be a straight line because I had a log there and I've just got an x there. So that's what we did. Now let's do it in practice with some experiments. Okay, my first experiment, flow rate through a water pipe, maximum flow rate. So here we have, so I'm going to vary the diameter of my pipe here, so in centimetres, 1 centimetre, 2 centimetre, 3, 5 and 10, and I'm going to measure the flow rate in litres a second. So here are the flow rates, and maximum flow rate is limited by surface friction on these, so in pipes. So I'm going to have some sort of power relationship here that I'm going to investigate. So my flow rate is some constant times the diameter to some power n that I need to find. And if I just graphed that as it was, I'd get a curve like this graph on the right, but I want to get a straight line, so I'm going to log this equation. On the left hand side I'm going to have log r, which is going to become my y for my graph. I've got log k on its own, which is just some sort of constant, so that's going to be my plus c. And over here my final term is n times log d. Now d is my variable, so log d is the bit that's changing, so that's going to be my x, and n is some multiplier at the front, so that's going to be my m, isn't it? So what have I got? That's my y equals mx plus c set up. So what do I need? In order to graph this, then I need the values of log r and I need the values of log d. So what would we do? We'd extend our table and calculate the values of log d and log r, put them into the table for each value or each calculation, yeah, and then go from there. Now these days we're going to put that in our calculator, so let's get my calculator up to do my regression analysis. So I've put in the values here except for the last one. So we need to be clear that we're doing the log values because that's what we're going to graph. So I need in my x, in my first list, I need all the logs of diameter. So my last one is going to be the log of 10, log of 10. There we go. And my last y value is going to be the log of my flow rate. So that's the log of 199.8. There we go. So I've put in my data, and there's a two variable. I can graph that, so I'm getting quite a good straight line. I can now do my regression on that. It's going to be linear regression, and so I get this nice graph with the curve fit, don't I? There we are with my regression. Let's just get the numbers back on the screen. So I've used y equals ax plus b. So on my graph there, my gradient m is going to be the 3.9998. So rounded to 4 significant figures, that's 4. Yeah, so my pattern, that's going to be my power. We'll go back and just check that a sec. That's going to be my power, and my intercept is minus 1.6988. That's my intercept, yeah. So I read those two numbers off, my gradient and my intercept. Sorry, I can't show this at the same time on the screen. Well, what was my gradient going to be? My gradient here, m, was going to be my power, wasn't it? So n is going to equal 4. So we're in a power 4 relationship. Then I need to find what log k is. Well, log k is my constant, c, which we just read off as that. And I now need to know what k is. So k is going to be 10 to the power minus 1.6988. So k is going to be 0.02001. There we are. And it would create a graph if you did it by hand in your you'd get a graph that looks like that, log R against log D. So what's my experimental relationship? Well, R equals 0.02, I've just rounded that up, D to the power 4. There we are, that's my relationship. That looks like a general relationship, doesn't it, this D to the 4, that there's something going on there physically. And if I want to know what flow rate would be if my pipe diameter was 12, well, I'd just substitute 12 into that equation, that formula, and I'd get the R flow rate equals 415 litres per second. So that's a power relationship where we end up with a log-log. Okay, let's have a look at this one. Calling a coffee. So I make some coffee, it's boiling hot, and it starts to lose its heat. This is an exponential relationship because the heat flow is proportional to the temperature difference. So as the temperature difference drops, so the heat flow drops, so the temperature reduction drops, slows down, doesn't it? So what have I done here in my experiment? I've captured information here, so I've got at different times 2, 4, 6, 8, 10, 12, up to 20 minutes after the coffee's made. I've measured the temperature, so 81 degrees C, 70, 61, 52, yeah? So temperature's dropping. I'm assuming that I've got an exponential relationship, so my temperature is some constant times another constant to the power t, where t is time. So if I was just to try and graph that, I'd get a curve. I want to get a straight line so I can work out what k and a are. So I'm going to log this equation. So on the left hand side I get log t, log of temperature, that's going to be my y value. And I get a log k, well that's just a constant, so that's going to be my c. On the final term I've got t log a, well t is the thing that's changing, so that's going to be my x. And the log a is just a constant, so that's going to be my m. So as we can see, here is my y equals mx plus c. Okay, so what do I want to do next? Well, I need to get the data together that I need for this graph. Well, I already know what the t values are for my x-axis, but my y-axis is going to be log of t, so I need to find all those values, and I would normally put them into my table. And now I'm going to use my trusty calculator. So here's my calculator on the screen. I've entered in the first list the times 2, 4, 6, 8, 10, 12, and in the second list I need to enter in the log of the t value. So I've put most of those in. I'm now down to 18 minutes, so I need to put in the log of the temperature at that point, which is 24, so there's log 24, and my final one is going to be at 20 minutes. I've got the log of the temperature, which is the log of 21. So now I've got all my data in, and I can graph that, and I can calculate my regression line. Here we go, and I get a nice straight line. It's negative here because temperature's dropping, so we're in decay. So let's just put that up. Go back to the values. There we go. Okay, so I've now got my values. Well, what's my gradient? My gradient here is in the calculator is the a value, so that's negative 0.03311. So that's my gradient, and my intercept b is 1.9785. So how am I using those? Back on my screen here. Well, how am I using my gradient? Well, my gradient m is going to be the log of a, so therefore a is going to be 10 to the power negative 0.03311, so a is going to be 0.9266. What's my constant? How am I going to use my constant? Well, C, my constant from the calculator, was my intercept, is 1.9785, and that's going to be equal to log k. So therefore k is 10 to the power 1.9785, k is 95.17, that's degrees C, I think we're going to find, and therefore that's my relationship, yeah? T equals 95.17 times 10 times 0.9265 to the power t, and I can use that to predict future temperature. So what's the temperature going to be when t equals 30? Well, I substitute little t equals 30 into the equation, I get my temperature big T, which is 9.6 degrees C. And if you want to, you can do exactly this sort of thing with coronavirus data or any other sort of thing you're looking at. But that was quite timely when I was doing this video. So there we have it. Here's my summary page for you to pause and copy down. The important things to remember are we've got to decide at the start whether we're in a power or exponential relationship. Then we log our equation so that we've used, and we decide from the logs what graph we need to do. So on the left hand side I'm going to have a log graph because I've got a log on as my y in my straight line and a log on the right hand side as well. So that's going to be a log graph. Whereas in the exponential I've got log on the left hand side, but I've got an x on the right hand side of this equation, so I'm going to graph log y against x. You could then do a best fit line if you want, and by hand, and use that to find your gradient and your intercept, m and c, or you can put it in your calculator, which these days is what you can do in most of these exams, and this turns up in the pure exam and in the stats exam, so it's well worth knowing how to do it. And then we just work backwards. So from our relationships we can find out what our constants are in our relationship. So n will equal the gradient here, and k will equal 10 to the power of the constant, the intercept. So we can substitute those into y equals kx, and on this one a will equal 10 to the power of the gradient, and k will equal 10 to the power of the constant, the intercept. So there you have it. Best of luck.